Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, Dave Ansell and Chris Smith.
So, Dave, maybe you can help out James Mackin. He's from Marsh Green School, Wigan in Lancashire. He says, could we use nitrogen to freeze the Antarctic, and therefore prevent it from melting anymore?
So he's wanting to use liquid nitrogen, I guess, which is a very, very cold liquid. It's what happens if you take the air down to minus 200 degrees centigrade or so. It turns into a liquid, and then if he wants to dump that on Antarctica and stop it freezing. If you had a huge amount of liquid nitrogen, you could make anything you like very, very cold. Problem is that in order to make the liquid nitrogen, you've basically got to run a fridge in order to cool down the nitrogen and turn it into liquid nitrogen. Now, the problem is, if you use a fridge, you always get more heat out than if a fridge basically takes heat from something, your food, and dumps it out of the back of the fridge, which you'll always notice is hot. The thing is with fridges is you always end up with more heat coming out the back than you've taken out of the food. So if you're making all this liquid nitrogen to try and cool down Antarctica, you're actually going to make more heat wherever you're making the liquid nitrogen.
So whilst Antarctica will get colder, the rest of the planet somewhere is going to get hotter.
Yeah, the huge fridge is going to get incredibly hot, and it's probably overall
so
the world's
no such thing as a
warmer.
free lunch, basically, is there?
I'm afraid not, no.
All right, OK, that's answered that one. And thanks to James for sending it through as well.
So incidentally, yes, if anyone does want to write to us and send us any questions, that kind of thing, then you can email us during the week. It's chris@nakedscientist.com.
Hi to Marie, who says, Sue, please ask why is it when we bruise it is blue, as I believe to be broken blood veins, and blood is red?
Yep, you're right. It is a bit of a conundrum. Why should bruises be a funny colour? The person who asked that question, was it Marie? Is quite
Marie,
right,
yeah.
That when you damage a piece of tissue, what you do is to traumatise blood vessels, and the trauma to those blood vessels punctures them, and some of the blood, which is red, oozes out, and it goes into the tissue. Now, blood, when it first goes out into the tissue, is still in the form of blood cells, the tiny little red discs which carry the haemoglobin. That's the iron-containing pigment that is native red, and it carries oxygen around the body. But you'll have noticed that if you have a piece of meat which has been kept out of the fridge for a little while, it goes a bluey colour. And that's because when you take all the oxygen out of haemoglobin, or myoglobin, which is a related molecule in muscle, it goes from a red colour to a blue colour. And that's why someone who cuts off the blood supply to a part of their body for any period of time, the tissue turns a blue colour. You can do it on yourself if you put an elastic band around the end of your finger for a little while. You'll see your finger goes a blue colour on the end because the tissue uses all the oxygen from the haemoglobin, and the haemoglobin then changes colour because when it loses oxygen, the haemoglobin changes its shape very slightly. And this causes it to, instead of reflecting red light, which is why it looks red, it starts to soak up red light, and this makes it look more blue. So when you have a bruise and the red blood cells come out of the injured blood vessels into the damaged bit of tissue, to start with, the first thing that happens is that the tissue locally removes the oxygen from those red blood cells, and they change colour to blue. And that's why the first phase of a bruise is a blue or purpley colour. The next thing that happens with a bruise is that it slowly over time turns a green colour, and then a brown colour, and then a yellow colour. And what those colours are the breakdown products of the haemoglobin as the body's immune system moves in to clean up the damage and remove the dead cells that have resulted from the bruise. And one of the things that you see with bruising is that colour change, and that's because the haemoglobin molecule, when you break it open, turns into something eventually which is called bilirubin, and this is a browny yellow colour, and that's the colour that a bruise ultimately goes before it disappears, and the bilirubin slowly leaches away into the body. So that's why you get that nice colour change with bruising.
Oh, it's horrible. What about people who really bruise easily, or, you know, because some people do and some people don't. I bruise quite easily, and you just think, oh, crikey, you know, is there a long-term harm effect of that?
My wife, Sarah, bruises very easily, and as far as she knows, she's been doing it all her life and she's thoroughly healthy. That's not to say that some people who bruise very easily and suddenly start bruising very easily, having previously not bruised easily, haven't got a problem. In the bloodstream, there is a small family of particles called platelets. They're very, very tiny. They're about a tenth of the size of a red blood cell, and what they are little bits of cells. They're made in the bone marrow by a big cell called a megakaryocyte, and when this megakaryocyte breaks apart, it buds off little little blebs from its surface, and these are these platelets. And when they cruise around in the blood system, they're a perfect little sphere. They're nice and smooth and round. But where they hit a part of the body where the blood vessel wall is damaged, this activates them, and they go from being a smooth round shape into this very irregular sort of starry shape, a bit like a starfish. And at the same time they also pump out chemicals from inside them, and this causes them to become very, very sticky. And this blocks the damage to the blood vessel wall, and they form a platelet plug to stop you bleeding. Now, in some people, I think this process takes a little bit longer than in other people, and for this reason you can bruise a little bit more readily because it takes a little bit longer before the bleeding is contained. But in some people who have a pathological condition, if you don't have enough of those platelets, because, say, you have a bone marrow problem, then it can suddenly present as new, very easy bruising, and that's one sign that there's something wrong with you and you ought to get checked out.
Right, OK, thank you very much, Dr. Chris. Question, Dr. Dave. If two high-powered rifle bullets hit each other head-on, fired from 1,000-yard distance, what would happen? That's from Mike.
I guess the first thing is that if they were very, very squashy and they stuck together and nothing flew off, then if they're going the same speed, if they hit each other, then they'll just stop. Because the amount of momentum, one of them's got a certain amount of momentum going one direction, the other's got a certain amount of momentum going the other direction, so it exactly cancels out. They'll just stop and drop to the ground. However, I think it's very, very, very unlikely for this to happen because, for a start, they're made out of a hard metal, and instead of actually squishing into each other, they're much more likely to kind of ricochet off each other and fly off, either fall to pieces and fly off in various different directions, different bits in different directions, or just shatter, or just ricochet off each other and go off in slightly different directions.
All right, thank you very much for that. Right. Dr. Chris, another Mike asks, why does scratching an itch stop it?
It doesn't always, though, does it?
No, I know. I know. It makes me scratchy now.
It's a big question. Why do we have itches, including the 7-year itch? So itches come in lots of different flavours and types. But the point about itching is it's the body's defence mechanism, because it alerts you to an irritation on the surface of the body, that there's something going on there. And it's probably because the things that make us itch are things like insect bites or other parasites that are going where they shouldn't. And it alerts you to go and scratch that bit and detach or shoo away the insect that could be about to bite you and give you a disease. What's become apparent in recent years is that scientists have discovered a certain class of nerve fibres. They're very, very small, and they are specific for itch, so they just convey the itch sensation, and they unite with the spinal cord, and they feed a chemical into the spinal cord, which, whenever there's an itch in the patch that nerve supplies, they squirt this chemical into the spinal cord. And scientists have found that they can switch off itch if they block that chemical signalling pathway. So it seems that there's an itch-specific pathway into the nervous system, and when that's activated, you feel itchy. And looking inside the spinal cord, the reason a scratch seems to turn off an itch is in the same way that if you thump something and make an area of the body hurt, that you want to rub it better, and rubbing it better eases the pain. And we think it's the same, that when you rub an injured body part better, it switches off pain. Scratching a body part switches off itch. What scientists have found is that when you scratch something, what you're doing is triggering a small amount of pain in the area of the body that's got the itch, and the fibres, the nerve cells that signal the pain, feed back into the spinal cord, and they gate or shut down the nerve cells that are carrying the itch sensation, so it switches off the itch, and that's why scratching feels so good.
All right, Mike, I hope that's answered your question. And let's go to the phones now, because Jill is on the line. Hello, Jill.
Hello, good evening, Sue.
Hello, you're through to Dr. Chris and Dr. Dave. What's your question?
When somebody dies and they are cremated, how do we decipher, or how do we separate the ashes from, like, the coffin, if you know what I mean? How do you separate the body from the coffin? How do we know?
Well, the answer is that it's very difficult. And if you look at the amount of stuff that's in a body, the vast majority of our body weight, unless you're incredibly fat, is actually water. So when you put that into a cremation, then most of that water just evaporates off and goes up the chimney as steam. And so what's left behind is the stuff that either doesn't burn and turn into a gas, so the incombustible material, and also other traces of things that are in the body that you can't vaporise very easily. So in fact, the amount of stuff that's left behind is very, very low. Depending upon what you put the body in when you cremate it, the amount of ash that's left will make a bigger or a smaller contribution to the amount of ash. So this is not necessarily the best way to get rid of yourself from the perspective of the environment. And people in Scandinavia have realised this, and so there's a programme running, I think it's in Sweden, where what they've been doing is investigating how you could blast people to pieces with ultrasound. So what they do, Dave was talking about liquid nitrogen earlier, you would take the person's body, you put it in liquid nitrogen so it goes down to minus 200 degrees C, and in the same way that in the cartoons you see people smashed to pieces when they get hit by a hammer when they're frozen. Well, the scientists there and researchers there are using sound waves to blast a body to pieces, and it turns into a fine dust. And this is just the body. You haven't got any contamination from the coffin or anything. It's just a fine dust of what's left of the body, and then you can scatter that on the ground, and it's much better for the environment, because to cremate a body uses about the equivalent of 10 gallons of diesel. So obviously that's not good for the environment. So if you want to be really environmentally friendly, get sonicated to death in Sweden.
All right, Jill.
So really what you're saying to me now, the answer, the question that I've asked, there's not much of a person's body left in the ash.
No, it must be. It's going to be less than about half their body weight, because when you put someone into an incinerator, if you look at the average, say, 70-kilo person, a good 40 kilos of that body is water, so that will just evaporate.
I understand.
Some of the other parts of the body will react with oxygen and other gases, and they will turn into gases themselves, like carbon dioxide, for example.
And bones?
Exactly. And there will be some material left behind, in the same way as when you burn coal on your fire or wood, you get some ash left, and that's the incombustible. It doesn't turn into gas very easily. That's what gets left behind when you incinerate a human body, and that's what you get back from the crematorium, but it will be mixed in with traces of whatever coffin you had, for instance.
Yeah.
All right, Jill, thank you very much indeed. Thank you. Bye-bye. Now then, the tabloids have had photos of a human figure on Mars. Apparently, would this be possible? And if not, why not?
I mean, it would be impossible for a human to survive on Mars, because there's only 1% of the atmosphere on Mars than there is on Earth, so it's almost like going out straight into a vacuum. And also, what atmosphere there is carbon dioxide, so we wouldn't be able to breathe. I think a few years ago they saw a face on Mars. Lots of people saw a face on Mars, and everyone got really excited about it. And I've just found this picture of it does look, especially look from quite a long way away, this picture of a person. It does look a bit like a person sitting on a rock, but as you get up closer, it looks a lot more like a shadow. I think this sort of thing's actually telling us a lot more about our brains than it is about Mars.
It's a woman on Mars, isn't it?
Because basically our brains are incredibly good at seeing especially faces and also human figures in just about anything, because it's very, very important to us. Other humans, very important. So if you see in sort of the mist, sort of 3 miles away, kind of several hundred yards away, something that looks a bit like a human, it might be, and it's important to know that, especially if they might be coming to attack you or something, or they're just very interesting. And so if you look at enough pictures of anything, eventually you'll see some bits of either faces or bits of body, or you'll just see things because your brain sees things which aren't there because it's so good at seeing patterns.
Like the magic pictures, then. Right, next up, Bob has said, annually, does the whole world receive the same amount of light and darkness?
If the world was a perfect sphere and perfectly smooth, because it's spinning, then every part, and there was an atmosphere, and then every part of it would be light and dark for the same amount of time. However, the thing which doesn't mean that doesn't quite work is if you've got hills. Because if you're at the bottom of a valley, the sun's going to set earlier for you because you're going to be going to the shadow of the sides of the valley. And if you're at the top of a mountain, then the sun's going to shut a bit later. So tops of mountains and bottom are going to get a bit more sunlight. Bottoms of valleys are going to get a bit less time, less daylight. But of course, the equator, although it has the same amount of daylight as we do, when it's there, the sun's much stronger, so they get more heat.
Right, OK, so that's answered that one. Now, David from California sent an email to say, what happened to all the promise of cloning that was so highly touted a few years back? Why are we still not able to get a brand new heart or kidney via cloning?
Well, when we talked to the guy, Ian Wilmot, who was responsible for making Dolly the sheep, and it was interesting, I was sorting out my back room last weekend and I found the original press cutting from one of the broadsheet newspapers from 1996 when Dolly the sheep was unveiled. And I was amazed to think, wow, I've still got this bit of news cutting. But one of the things that people thought was, wow, this is it. We can start making clones of humans, other things. This will give us lots of stem cells which are genetically compatible with the organ or person that we want to repair, and then we'll be able to guide those cells to turn into what we want them to turn into, and as a result of that we'll be able to grow new body parts. It's been a lot slower than that because scientists have found there's been a number of stumbling blocks. Whilst we've been quite successful at cloning some animals, mice are relatively easy, rats and things like that are relatively easy, sheep and even pigs have been cloned, now cows have been cloned, and also stallions that have been gelded have been cloned in order to turn them back into stallions, because of course you can't breed from a gelding because it's minus one or two important bits of its anatomy. So by cloning it, you can get a breeding animal that's genetically identical to the one thing that you have removed. But they haven't succeeded with bigger animals like chimpanzees and humans until very recently. And what we think is happening with this, and let me just summarise, the way in which you clone something is you take an egg, such as that a woman ovulates every month, and the egg contains the woman's chromosomes, but if you remove those chromosomes, you can put inside that egg the complete chromosomes of the organism you want to clone. So I wanted to clone me. I could take an egg, I could take a cell from my skin which has the complete set of my DNA, and I could insert that into the egg. And there's something special about egg cells. They contain chemicals that can chemically reprogram DNA, and they can fool a mature skin cell into thinking it's an embryo again. And it switches on all of the right genetic programs and pathways to make that cell begin to divide and turn into a new embryo. And that's exactly how you clone things, but it's been very difficult to make that happen with bigger animals and more specialised primates like us and like chimpanzees. But now, in recent months, scientists have managed to do it. They have produced early embryos that have been cloned from monkeys and chimpanzees. This suggests that it could be possible to use the techniques in humans, but it's just because it's technically very demanding, and it's also ethically charged. People are not very happy to have you fooling around with potential humans, and for that reason there have been restrictions in place.
Now then, let's get to Vicky's question, who would like to know what is the weakest point in a suspension bridge, does not understand the construction of it.
Okay, a suspension bridge is the best designer bridge we've got for going a very, very, very long distance. It basically is, the basic design is to take a long rope, hang it between two towers.
Yep.
And then take it, and you could just put a roadway along the rope, but it would be really curved.
Yeah.
Because if you hang a rope, it's always curved, and the straighter it goes, the harder it is to pull it straight. So you want a nice curved rope so you don't have to pull too hard. And then you just hang a roadway underneath it off lots of smaller ropes. So you've got a roadway hanging from two big, long, heavy, strong ropes, and then that's a suspension bridge. I don't know if you've ever had two people playing a tug of war, and then if you try and pull the middle of the rope, it's very easy to bend the rope.
Yes.
A little bit, because the two people are mostly fighting each other, and your weight and your pulling they're not fighting you very much, so it's very easy to bend the rope. So that's the same thing with the suspension bridge. So if you put the weight right in the middle, that produces a huge extra force on the two major ropes. They're actually made out of wire. The two major cables, and so that's going to be the worst place to put weight on a suspension bridge. If you put it near the uprights, then the weight's only being pulling straight down on the uprights. So the uprights have only got to take the weight which you're adding to them. Whereas if you put it in the middle, it's going to be 10, 50 times more weight that the ropes have got to take. So the weakest place in the suspension bridge, the worst place to put weight, is right in the centre.
Right, don't break down in the middle then. Be worried.
I think you'd need to be a pretty heavy vehicle for it to be an issue.
There's quite an interesting thing with suspension bridges, which is that the wires, as Dave said, that they use are actually 50 centimetres in diameter, and they're not just a single cable, they're a whole host of wires wound together to make a sort of composite. And up in Scotland, they're having to keep a very close eye on the Forth Bridge and some of the other big suspension bridges that go across some of their big rivers, because the wires are now getting very, very old, and they're beginning to corrode and break. And the way in which they've begun to study how these wires are surviving or not, as the case may be, is by using the equivalent of a stethoscope to listen to them. And so they've sort of put these very sensitive microphones on the sides of the cables, and you monitor over time, and every so often you hear this very abrupt and very loud pinging noise, and this is one of the strands of the cable actually breaking. So over time they'll be able to work out how many cables or how many wires are broken within the cable, and therefore what the average lifespan of the cable is going to be, and when the bridge has to be closed, because quite frankly it's got dangerous.
Complex stuff as well, winding the wires in the first place. Now then, lots of toners tonight. Floaters in the eye, where do they come from and how can you get rid of them?
OK, well, this is because of various reasons, actually. Your eye is a bag of fluid, and if you look at the front of the eye where the lens is, that's the anterior chamber, and you're continuously making small amounts of fluid there which filter around your lens and then get reabsorbed back into the blood circulation. But behind the anterior chamber, in the posterior chamber, is the vitreous, and this is a kind of jelly-like material, and it's chosen appropriately because it has the right refractive index. In other words, it bends light the right amount so that it complements the optics of the front of your eye, the cornea and the lens, to focus light straight onto the retina, which is the light-sensitive patch of tissue right at the back of the eye. And the point about this is... I've totally forgotten the question.
It's about floaters in your eye.
That's right.
Yes. What are they and how do you get rid
where
of
they
them?
actually come from?
Yeah, where they come from.
The vitreous fluid right at the back, because it's a jelly-like fluid, things can move through it. And when your eye is being put together as a baby, it has to develop from cells which are growing on the... Actually, your eye develops from your skin, and the nervous system underneath the skin on the front of the developing face induces the skin cells to turn into the lens, and they then unite with the underlying central nervous system tissue, which becomes the retina. So this has to remodel a lot as you're developing as a baby, and some of the tissue that doesn't eventually turn up and ends up having to break down to become the eye can leave these vestiges in the eye, little bits of blood vessel or bits of cell which take a little while to disappear, and they can float around in there for a while, and they can be these tiny floaters, these specks that you see drifting across your vision from time to time. So that's one reason. The second reason is that it can be a sign that things are amiss with your eye. If you suddenly get a new surge of new floaters, this can be a sign of a hemorrhage into the back of the eye, because sometimes there are some conditions, and diabetes is one of them, and macular degeneration is another one, and a detached retina, when the retina pulls away from the blood vessels at the back of the eye, that can be another one. These conditions are associated with a bleed or a leaking of blood vessels into the back of the eye. And what you're seeing as these little specks floating around are actually physically blood cells and signs of the inflammation that accompanies that. So sometimes it can be perfectly normal. If it's something that's not changing and it's something you've had for a long time, it can be a vestige of how your eye developed. And the other possibility, if it suddenly occurs and it's very bad, is that it can be a sign that there's been a hemorrhage in the back of the eye or something's amiss. And if you see that, then you ought to go and see your doctor.
Thank you very much, Chris. Now then, Dr. Dave, an email here from Simon in Kings Lynn. Hi, Sue and clever doc people. I'd like to hear an explanation for the old theory that when a fly flies into a train windscreen, it actually stops the train moving for a split second. The idea being that the fly changes its motion from one direction to the opposite direction, so at some point it must be stationary. Therefore, the train which is in contact with it must be stationary too. Does the fly stop the train?
I think in all cases it won't, but I think what it's coming from is that if you imagine that the fly was perfectly hard and the train was perfectly hard as well, so they don't deform at all. When the fly hits the train and changes direction, it's going to change direction in an infinitely small amount of time. It's going to do it instantaneously, and that's going to require an infinitely large force. Absolutely enormous force to be able to accelerate that fly from one direction to the other one instantaneously. And so the idea is that you apply an infinitely large force against the train, so it must stop the train. But actually, the way because the infinitely large force is for an infinitely short period of time, it doesn't actually have enough oomph to it to actually stop the train, even for a tiny split second.
I was going to say, that's a good thing, isn't it? Because trains are slow enough as it is.
Indeed. And actually, in reality, there's no chance it would do that, because both the fly and the train will deform. So instead of having an infinitely large force, what you'll actually get is a smaller force for over, maybe a millisecond, a microsecond, maybe a millisecond or so would probably take to squash a fly if the train was going very fast. And so it has quite a large force, but not a huge one, which will just slow down the train a little bit. It will slow down the train a bit, but not very much. And then the fly will carry on with the train.
Formula One car engines generate 1,000 brake horsepower. How is this measured?
It's all to do with how powerful an engine actually is. It dates actually ancestrally from mine engines and things like that. And in those days, the definition of 1 horsepower was that it could lift 33,000 pounds in a minute. But you could consider it another way. That's about 250 kilograms over 30 centimetres in about a second. Or to put it another way entirely, it's about 740 watts, so 3/4 of a kilowatt. So 1 bar on your electric fire is a kilowatt, and 3/4 of that is 1 horsepower. So when you're talking about engine output, you're working out how much power the engine is producing by burning fuel. And all those Formula One cars are actually supercharged or turbocharged, so they produce huge amounts of energy. And by working out how fast the car accelerates, you can work out how much energy is coming out of the engine, and therefore you can work out what its brake horsepower is.
Yeah, horsepower is a measure of power rather than energy, and power is the amount of energy you use every second. The way they practically do it on an engine is they basically attach it to a brake, as the term brake horsepower implies. So you get the engine, attach it to a big brake, and then you run the engine up, and then you apply the brake to it, so you can measure the force which the brake is applying to the engine to try and slow it down.
Oh, right, yeah.
You know how fast the engine's going round.
Yeah.
So, in fact, it's a torque which you're measuring. So you multiply the torque by the number of RPM the engine's doing, and that gives you a power. Then you multiply by a couple of factors, and you'll end up with the number of horsepower the engine's producing.
Gosh. Now, then, another bruising question here. Graham asks, why has he bruised after a routine blood test when he normally doesn't?
Oh, it's just because the phlebotomist or the doctor, probably the doctor because they don't do it so often, wasn't very careful. Because when you take a blood test, of course, what you're doing is trying to locate a vein below the surface of the skin, and then you go through with the needle through the skin into the vein, and the needle's hollow, and you draw and put a pressure on the syringe by drawing out the plunger, and this means the pressure in the syringe is now lower than the pressure of blood in the vein, so blood flows out of the vein and into the syringe, and then when the syringe is full, you let go of the tourniquet, which you try and apply on the upper arm, if you're taking it from the arm, and then withdraw the needle carefully. But of course you've now made a hole which is about 1 millimetre across in the wall of the vein, and you try and stop bleeding by applying pressure, usually by putting a blob of cotton wool or something onto the area, and the pressure reduces the blood flow, and it also encourages the platelets, which I spoke about earlier, to stick onto the damaged bit of blood vessel and to block it up. But sometimes if you move the arm very quickly, or enough pressure isn't applied, or the hole in the vessel wall is perhaps not straight into the vessel, it's gone sideways through the vessel a little bit and done a bit of damage on the way through, it can produce a bigger hole, and this can be harder to plug up. So you get a bit of leaching of blood from inside the vessel to the extravascular space, in other words, the tissue around the blood vessel, and then you've got a bruise, and it takes a little while for that to go away. But thankfully it's not harmful, and as far as we know, it doesn't actually do any long-term damage to the blood vessel to any great degree, unless you really go beyond the pale and are, say, an intravenous drug user, when introducing needles continuously into veins, and also the other things that you generally find when you buy street drugs, which includes talcum powder and brick dust, which is what unscrupulous dealers put into their drugs. This damages veins. Under those circumstances, different kettle of fish, but normally it shouldn't harm your veins, and the bruise will just go away.
Right. Thank you for that. Now then, Dave, one for you, I think. Why do fluorescent tubes last a lot longer than normal light bulbs? Ian says the tube in his kitchen has gone on for years and years with no problem, but he's always changing light bulbs.
They both work on two very different principles. The way a normal light bulb works is it's just got a very, very narrow wire. If you ever look very carefully, you can see the filament. It's a very narrow wire wrapped up into a coil, and sometimes a coil in a coil. And then you put electricity through that and it gets hot. If something gets hot enough, it starts to glow. In fact, everything glows all the time, but when it gets hot enough, it starts to glow in a colour which you can see. And if it gets really, really hot, it glows white. They make this coil out of tungsten, which is a metal which has a melting point of about 3,400 degrees centigrade and a boiling point of about 5,500 degrees centigrade. But even though the boiling point's that high, it's running at 2,000 degrees centigrade normally. So even though it shouldn't be melting or boiling, some atoms of tungsten will kind of evaporate off in the same way as if you've got a bowl of water, even though it's not boiling, it'll evaporate slowly over time. And the tungsten in your light bulb will evaporate slowly over time, and gently it evaporates and deposits itself onto the glass envelope, and eventually there's no wire left, and then it blows, and then you haven't got a light bulb anymore. A fluorescent tube works on a different principle. That works in general, it's a lot colder. It's got gas inside it at quite low pressure. You pass an electric current through that gas, and it gives the atoms inside that gas lots of energy, and then when they release that energy again, it's as ultraviolet light, and then that makes the surface of the tube glow. In the same way as if you've ever been out to a club or something, the ultraviolet light goes on your clothes, they glow. And so there's that white stuff on the inside of the tube is a phosphor which glows when the ultraviolet light hits it. And although the ends of when it's starting, the ends of the tube have to get quite hot to start the process off and start the current going through the gas. But once it's starting, once it's running normally, it's not running very hot, so there's nothing really to go wrong. It'll take years and years and years before you get a similar problem to a normal light bulb, probably tens, if not hundreds of years of continuous use. So the only thing which wears them out is turning them on and off.
So which is more energy efficient then, the fluorescent or the normal light bulb?
The fluorescent is much more energy efficient. In fact, I've made a beautiful thing this week which actually shows that.
A beautiful thing?
A beautiful thing. I got a webcam and took out a filter which stops the infrared light, which is a light you can't see, and instead put a filter on which stops visible light. You can actually use a piece of film which has been exposed, and you can look at things. And if you look at a fluorescent light bulb in the infrared, which you can't see, it's very, very dim. You can't hardly see it at all, and the room looks pitch black if it's lit by a fluorescent light bulb in the infrared. But if you look at a conventional light bulb, it's incredibly bright, and the room's really bright in infrared, so it's wasting 90% of its energy putting out a colour of light which we can't see.
All right, OK. One last one here, a follow-up to cremation and ultrasonic, is that white is not good. To stick your hands in the running ultrasonic tank damages your fingers and joints, says John in America.
Yes, the way in which these ultrasound systems work, there's something called a sonicator. And when you're using instruments, say you've been using an instrument we used to do dissections, for example, and when you're using very fine instruments, you can get bits of tissue in the metalwork of these very fine instruments, and obviously if you were to put them away like that, the water that's trapped into the bits of tissue could come out and then cause these very expensive instruments to rust. So a good way to clean them up is to put them in a water bath and then sonicate them, and this blasts the instrument with very high frequency sound waves. It's very, very high frequency, so in other words your ears can't pick it up because the ears don't respond at those frequencies, but the energy of the vibrations causes the tissue to try and bounce backwards and forwards, so vibrate so fast that it causes the material to fall apart, and it breaks the material up into lots of tiny fragments which are easily detached from the surface of the metal instrument, and this is how you clean them up. Now the consequence of putting your finger into that is that all that sound energy would be directed into your living tissue. The tissue would try and vibrate or move at the same rate as the sound waves, and so it would literally try and tear your body apart. And it is possible to do this. You can in a nightclub, if you had a loud enough sound system, you could actually cause people's bodies to start vibrating themselves to pieces, but I wouldn't advise anyone to try and do it.
Crikey.
But yes, you could physically do injury this way, and in the same way that the body, instead of being cremated, can be sonicated to pieces, the same thing would happen to your body if you put yourself alive in the sonicator. So I wouldn't advise anyone to do that, but it is a very good way to clean things up.
Because if people use a lot of vibrating machinery, don't they get white finger, which is a similar sort of thing?
Yes, I don't think that's entirely well understood, but there is a condition called vibrating white finger, which people who use a lot of road drills or miners who are drilling into rocks in mines used to get this. The continuous vibration seems to in some way damage the nervous system, and it causes an increase in the activity of the nervous system called the sympathetic nervous system, which controls how big your blood vessels are. And this causes the blood vessels to clamp down, restricting the flow of blood into the tissue, and it can make the tissue go white because there's no blood going into it, and very, very painful. And we think it's a sort of reflex sympathetic dystrophy is another word for this, and it seems to be associated with injury and also, as I say, chronic exposure to vibration.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.